Hello and welcome to this lecture. Today we'll learn about errors in the numerical methods or numerical analysis. So there are three kinds of errors while computations. First one is inheritance error. These are daily life errors of like errors in the machine. If a scale in a scale the point of zero is somehow what not in its actual position, then the error which arises is called it's kind of a inherent error. You may calculate the do the calculation how much correctly you want, but this kind of errors will never go away. This will stay. Next one is which comes into play is, and that is the second kind of error, truncation error. Let's say we are expanding e to the power x in the form of Taylor series. And then it will become 1 plus x by 1 factorial by x square by 2 factorials plus dot 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 x to the power n by n factor plus dot dot dot. This expansion is continuing up to infinity. But if this value of x is say something like 0.1, then e to the power 0.1 becomes 1 plus 0.1 by 1 factorial plus 0.1 whole square by 2 factorial plus 0.01 whole cube plus 3 factors. Now we see as we go forward and go to the next terms, the value of these values will become very less due to the higher power of this higher power of decimal value, and again there is a increasing value of the denominator. So in many cases we just take e to the power x is nearly equals to 1 plus say take first three terms x by 1 factorial plus x squared by 2 factorial. So in this case, an error will act there will be an error because the actual it will go away from the actual value, and this is the approximate value. Then the error is what? The actual value that minus the approximate value. We take the mod because we want to know the magnitude of the error, not whether it is negative or positive. So transgression error can be written as TIN CTI1 x minus mod of x minus x minus mod of x, where mod of x is the estimate value and x is the actual value. Means we are determining the magnitude from the original value, the magnitude of deviation from approximate value from the actual value. We can say like this. And error during round of errors. Say we're rounding off a number 1 by say 1 by 3. This will be this the original value of this become or say 10 by 3 or 1 by 3 or 1 by 3. This value becomes 0.33333. In many cases we just take 0.3 or 2D replaces and 3D replaces. So this is obviously not equals to this value. So there will be an error in between the approximate value and this original value. So this deviation can be written as like this. So this is the error caused during rounding off. Okay. Now there are in measurements of error. The topic comes as measurements of error. And another thing comes of loss of significance number, but in your syllabus, what I've seen for BCA, there is I don't think the loss of finding out of significant figures which you have already studied in class 9, 10 is there, so I am not talking about that. Because basically, if you just take some signal, basically you take only the significant value of a number, then there might be an error. You can understand that. Hopefully I can understand this base level. If you just take a significant value of a number, there may be an error arises. May or may not be. In case of basically in case of decimal value, there arises only. No, in just non-decimal value, they can't arise, right? So now how to measure these errors? So I have also told you in this lecture, I have given you an idea of loss of significance. Okay. So there are three kinds of measurmental errors. Number one is absolute error. The formula can be said as e to the ea equals to x minus x star, where x is the true value, obviously, x star is the approximated value, and e to the power a is the absolute error mod of e to the relative errors, the value of relative error e to the power r, where the real value x is not equals to 0, we have to take it x is not equals to 0. The approximate was said x star to relative error is x minus x star. This is something like finding out ratios and proportional relations by x. And the percentage of there's a finding out the fraction for of deviation, finding the ratio of deviation, something like that. And that's next comes percentage error. Obviously, we just have to multiply it by 100, e to the power r by 100. Then we will get percentage error. Which so this can be also obviously written as x minus x star by x. By x is obviously the approximate, the real value, and x star is the approximate value. Okay. Now there are many theorems, but we will not discuss about them in this lecture. If I have time, I will make another lecture where I will discuss about this theorems. So let's get straight into some problems. So problem number one. So problem number one states first. Find the absolute relative, and percentage errors of 1 by 3 if approximately taken as 0.333. Now we know the exact value is x equals to 1 by 3. The extra approximate value is obviously 0.333. So we know what absolute error e to the power a equals to x minus x star, which will be equals to 0. Say I'm taking just 5 digits, 3, 3, 3, 3, 3 minus 0.333. I have taken one extra v. The infinite trees, right? So this is nearly equals to, we can say, if I take just the first 5 threes, 0.00033. This is our absolute error. Now the relative error will be what? There is infinite trees after that. You can understand that. The relative error will be what? E to the power equal r. So x minus x star by x, which is obviously equals to is 0.0033 divided by 0.333, which will be equals to, check your calculator, the value will be equals to nearly equals to 0.001. Again, the percentage error, which is denoted by e to the power r, will be just, we have to just multiply 100. I'm just simplifying this. For percentage error, I'm writing this is e to the power r into 100. So this will become what? Equals to 0.01%. Check your calculators, you'll find out the value. Now, the next problem, this says find the relative percentage error in a approximate representation of 5 by 6. 5 by 6 is approximated as 0.8333, 33 times. It's 0.83333. So obviously the exact value is 5 by 6. At the absolute value, it's 0.833. So percentage error will be equals to e to the power p equals to, oh, we have to first calculate 5 by 6. 5 by 6 is equals to, we take decimal 0. 6 8 is 48. 20. What's the 6 4s and 6 3s. 6 3s 18, then 2 0, and again 3s 20 20. So 5 by 6 is like this, 0.83 is continuing, or this can be written as 0.83, the recurring number. So e to the power p can be written in the relative error, can be written as 0.83333 minus 0.833. In a similar way, if we take this as 5 plus 5 threes, then value will be look like some, and by 5 by 6, the value will look like something. The top will look like, the value of the numerator will look like 0.033. Nearly about approximately by 5 by 6. If we do it in the do the calculation in the calculator, the value will be 0.04. Next, they have given rounding off. We're rounding off to numbers. We have to know how the basic rules of rounding off to numbers. I'm telling this basic 4 rules of rounding